So in this and the next few classes, we'll basically be exploring optimal or near optimal prefix-free codes, and we want efficient prefix-free codes. So far, we have seen two algorithms. One is the Shannon code, wherein you first compute the lengths of the code words based on their probabilities. So this is so the length for a particular symbol x is the ceil of log of 1 over p of x. And using this, you construct the binary tree and assign code words based on these lengths. All right, so that's one approach, and we know that this is not too bad. It is going to be within 1 bit of the entropy. The second approach that we have seen is Huffman codes, wherein the approach is a little bit different. You always take the two least probability symbols, merge them to form a super symbol, and you apply this operation recursively until you just get one particular symbol. So this gives a particular code tree, right? So we'll first just see a couple of examples to also understand some of the properties of the Huffman code. And we'll also see what it looks like for the Shannon code. So let's take one simple example just to make sure that we've all understood this properly. Let's say that the distribution we have, Px, is say 0.25, 0.2, 0.15, 0.15. So there are 5 symbols in the alphabet, and the corresponding probabilities are 0.25, 0.2, 0.15, 0.15. Okay. All right. So what's the first step? Let's proceed with the Huffman coding method. The two least probability symbols are D and E. Combining them gives a super symbol, DE with probability 0.3. The next two least probability symbols, .25, 0.2. You see that B and C are the least probability symbols at this stage. So we'll just merge them. And the remaining are as it is. Now the two least probability symbols are A and DE. So we'll merge them. And finally you merge everything together. All right. So let's also assign code word bits. Say this is 0, 1, 0, 1, 0, 1, 0, 1. So 0 corresponds to BC and 1 corresponds to ADE. Right, so this is the code word tree corresponding to the Huffman code. Yeah. What do you mean ADE above BC? Correct. So basically, this brings me to the following point, that the Huffman code for a given distribution is not unique, right? Because just as we saw here, a relabeling of just using a relabeling, or in other words, the order in which you place these two symbols can give you a different code. But no matter what you do, I mean, at least this sort of reordering doesn't change the set of code word lengths, right? Even if so even over here, if I placed ADE above BC, then the first bit would change, but the code word lengths for A, B, C, D, and E would still remain the same. Okay, both of them are valid Huffman codes. All right. But later on we'll see that even the set of code word lengths may not be unique for Huffman coding. We'll see an example soon. Any other questions?
Wouldn't they be preferring to give 0 to 1 with the high probability?
That's okay. I mean, that's one systematic way of going about it. But it's still a valid Huffman code.
It's not mandatory to keep highest probabilities of assigning 0 and lowest probability.
Not necessary. They're both effectively Huffman codes. All right. But yes, that is a more systematic way of going about it. That is, you always place them in decreasing order of probabilities, and you assign 0 to the one with higher probability and 1 with the lower probability. All right. So if I did that, the corresponding code tree would look a little bit different. Even though the lengths are the same, the code trees can be different. So this is what the code tree would look like. Maybe I shouldn't draw a node. Right, so if I placed ADE above BC and assigned code word bit 0 to that, then the resulting code tree would look something like this. Okay, so the code tree can look different, but nevertheless the code word lengths are still the same. So these two code trees, these are both Huffman codes. And they're said to be length equivalent. That is, they have different code words, but the code word lengths are just the same. Any questions?
Is length equivalent for a given? Is it for each symbol or in general the set of?
Okay, so length equivalence is a more general concept. If you take the set of lengths of one code, it is the same as the set of lengths of another code. So two symbols may get different code word lengths, but still that's okay. Any other questions? Okay, so for the same, let's also try to construct the Shannon code. Okay, so these are the probabilities. Corresponding to these, we have to compute code word lengths. So let's try to do that. Right, so it's I had to do it. See. This would be 1 by the probabilities. Right, so it's 2, 3, 3. All right. So that would be the code word lengths would be 2, 2, 3, 3, and 3. All right, because the seal of log 1 by 0.15 was turned out to be 3. The same happened for 0.2, and for 0.25 it was just 2. Okay. So how do we go about constructing the Shannon code? You start with the increasing code word lengths. Start from the root, traverse the left of the tree until you go up to depth 2. So you have one code word, you assign this A. The second would be B. Now I need 3 code words of length 3. All right. So the third I have 1. Zero, 0. I assign code word C to this. D and E. Right, so this would be the Shannon code for this particular distribution.
And this need not be.
Again, this need not be unique depending on how you order them. So for example, I could have assigned this to B, this to A, or again there could be a relabeling depending on how I traverse the tree. But again, one systematic way is to always do it in decreasing order and always go to the left. Okay. So, nevertheless, whatever happens, you will get a prefix-free code, and these will be the lengths. The lengths will be the same. So this gives the Shannon code gives code word lengths 2, 2, 3, 3, and 3. But the Huffman code gives code word lengths 2, 2, 2, 3, and 3. So clearly the Shannon code is suboptimal, and you can also see from the code tree itself that it's suboptimal because at least for this symbol E, you could have assigned a shorter code word. But even assigning this a shorter code word doesn't make it optimal. It's still worse than the previous one. So if I constructed this new code, which is not a Shannon code by the way, I assign code word lengths 2, 2, 3, 3, and 2. Even then, this would not be optimal. This would have a code. This would have an expected length, which is larger than the expected length of the Huffman code. All right. So just to see this.
The lengths are similar.
Okay.
Why is Shannon code similar?
That's because, well, firstly, these lengths don't correspond to the Shannon code, right? I am kind of trimming the Shannon code. But this has a larger code word length, larger expected code word length than the Huffman code, because in this case I've trimmed the symbol E, right, which has lower probability. Okay, let's just calculate the expected length. Maybe that will make it clearer. So the PMF is 0.25, 0.25, 0.2, 0.2, and sorry, 0.2, 0.15, 0.15. Right, and the Huffman code, the lengths were 2, 2, 2, 3, 3. Is that correct? Whereas for the Shannon code, they turned out to be 2, 2, 3, 3, 3. And for the trimmed Shannon code, it was 2, 2, 3, 3, 2. So the expected length for the Huffman code is basically so it's 2.3 bits. For the Shannon code, it turns out to be 2.5 bits, whereas for the trimmed Shannon code, it's 2.35, right, which is worse. And really the reason is that the reason is because we are trimming E. If there were a way to trim C instead of E, then we would get the same expected length as that of the Huffman code. So this trimmed Shannon code is also length equivalent to the Huffman code, but it doesn't have the same expected length. All right. Any other questions?
So as long as we keep the prefix-free code and the length of the symbols are what is given by the formula, it's an code.
Yes. So the lengths have to be exactly C of log 1 over P of x. Only then is it a Shannon code. Okay. So we've seen that we can have two different Huffman codes that have the same set of lengths. All right. But in fact, it turns out that there can be two different Huffman codes for the same distribution without the same set of lengths. There can be different sets of lengths, but the same expected length. All right. 0.1, 0.2. Point 3. Right. 2. Let's see if I get it right this time. So I have I have 6 symbols, A, B, C, D, E, and F. And these are the probabilities, 0.3, 0.2, 0.2, 0.1, 0.1, and 0.1. So first I combine E and F, the two least probability symbols, to give me a super symbol EF with probability 0.2. Now I have 4 symbols, 0.3, 0.2, 0.2, and 0.1. Now I can make a number of choices. I can decide to merge this super symbol and this super symbol, or I can decide to merge this super symbol and this super symbol. All right. So let's say I merge these two. 0.3. The next step, I merge these two. Sorry, 0.6 and 1. Right? So the code tree would look like so sign 0, 1, 0, 1, 0, 1, 1. Zero zero would be B, 0 1 would be C, and I have 1 1 0. One, 0 being D, 1 0 being A, 1 1 1 being E and F. Because this is one Huffman code. All right. Let's try to construct this in a different way. So as earlier, I merge these two symbols to get 0.2. But now I'll choose to merge these two symbols instead. And then the rest is the same. Okay, great. Right, so this is still the same Huffman coding procedure, except that at an intermediate step, I had different choices or different ways where I could merge the two least probability symbols. There were at least 3 symbols with the same smallest probability, and I had a choice to make, and I made a different choice this time. Now let's draw the corresponding code tree. Let's label the symbols first. 1, 0, 1, 0, 1, 0, 1, 0, 1. So I have 0, 0 being A, and 0, 1, 0 being C, and 0, 1, 1 being D, and on the other hand I have 1, 0 being B, 1, 1, 0 being E, and 1, 1, 1 being F. So for the same symbols, the code word lengths are two, 2, 3, 3, 3, 3, right? Whereas here, I have 2, 2, 2, 3, 4, and 4. Right, so these two codes, both of them were obtained using the same Huffman procedure, but they're not length equivalent. In one case, I get the code word lengths 2, 2, 2, 3, 4, 4. In the other case, I get 2, 2, 3, 3, 3, 3, 3. All right. So I can't get the other code just by relabeling the code words. Let's compute the expected length in both cases. So the PMF was 0.3, 0.2, 0.2, sorry, can you remind me what the probabilities were? 1, 1, right? Correct. And the lengths in the first case were 2, 2, 2, 3, 4, 4. So these are the code word lengths for the first Huffman code, and the code word lengths for the second Huffman code were 2, 2, and then 3, 3, 3, 3. So in the first case, the expected length is 2.5 bits. The second code as well, the expected length turns out to be the same. So they have the same expected length, but different code word lengths. Right? So you can have two codes where the individual code word lengths are different. They have the same expected length, and they're both obtained from the same Huffman coding procedure. All right. So it's not just that a distribution can have two different Huffman codes of different code words, not just by relabeling, but they can also have different code word lengths. Right. Any questions? Okay, so far I've been saying that Huffman codes are optimal, but we haven't really seen that, we haven't proved that these codes are optimal. So let's try to go ahead and do that. So far we've also seen that, so given a particular code, a prefix-free code, you can get another code by relabeling or doing just some modifications to the tree. Right? We saw that essentially that is what is happening in the two different Huffman coding procedures. So then it's not so easy to prove that Huffman codes are optimal, right? You need to first think about what kind of labeling you should choose for the given prefix-free code. All right. So we'll first look at this class of canonical codes, which are Huffman, which are prefix-free codes with a certain, which are optimal prefix-free codes with a certain property. Sorry, let me put the following. So for any distribution, there exists an optimal prefix-free code, optimal in the sense of minimizing the expected length, which has the following three properties. So if you have two symbols, x and x prime, such that the probability of x is greater than the probability of x prime, then the length of the code word corresponding to x cannot be any more than the length of the code word corresponding to x prime. Which is natural to expect. If the second the two longest code words have the same length, and the third is that the two longest code words differ by only the last bit and correspond to the two least probability symbols. Okay, so what I'm saying is that there is an optimal prefix-free code that satisfies these three properties. It doesn't mean that all optimal prefix-free codes must satisfy all of these three properties. Okay. The first property is obvious. In fact, that has to be satisfied for every optimal prefix-free code. Why not? What happens if the first property is not satisfied?
You can come up with a problem that satisfies this, which will have lesser variables.
Correct. So if let's say that you have x and x prime, for which, so if one is not satisfied, then what we can do is you just replace the code words or exchange the code words for x and x prime. All right. So the expected length, the original expected length is sum overall x p of x L of x, which I'll separate out, which is some quantity L plus p of x L of x plus p of x prime L of x prime. If I exchange the two code words, then the new code word length, the new expected length is, it's the same for all of the terms corresponding to the symbols other than x and x prime remain the same. I'm not touching them. But the length of x, the new length of x would be L of x prime. And the new code word length for x prime is L of x. Right, because we've exchanged the code words corresponding to x and x prime. So the difference now is this particular quantity, right, which is p of x minus p of x prime times L of x minus L of x prime. But what did we assume? We assumed that p of x is greater than p of x prime and L of x is less than L of x prime. Right. So if p of x is greater than p of x prime and L of x is strictly less than L of x prime, then the right hand side,
But the
which one?
L of x should be greater than L of x.
Sorry.
P of x prime minus L of x.
Yeah, you're right. And L of x is greater than L of x prime, then the RHS is less than 0, which means that the new expected length is strictly less than the expected length of your original code. But then we assume that the original code was optimal. which can't happen. Right? Any questions? Okay. So every optimal prefix free code must satisfy the first property. What about the second property? The two longest code words must have the same length. Right? So let's take the two longest code words, and suppose let's say that x and x prime L of x and L of x prime are the longest. And let's assume that L of x is strictly greater than L of x prime. Okay. So this means that there is one code word whose length is greater than the code word for all of the other symbols. Right? Strictly greater. Correct? Do you agree with me? So there's one symbol which has a code word that is longer than all of the other code words. So if you think of the code word tree, right? You have some code word tree, something, and there is this code word for the symbol x, which is longer than everything else. So if you look at its, so this node, which corresponds to the symbol x, if you look at its parent, right, the node that is right above it in the code word tree, the parent has only one child, which is x. Or in other words, this symbol doesn't have a sibling. So a sibling is basically another symbol, another node which is at the same level and has the same parent. All right. So this doesn't have a sibling, which means that I can reduce the code word length for this particular symbol by 1 and it still remains a prefix free code. All right? Because what I can do is I can delete this particular node and assign this node to be the symbol node for x. Do you agree? I don't see a lot of confidence. Okay. So there's one symbol which has a longer code word length, strictly longer code word length than all of the other code words. Okay? So if this has to happen, then it must mean that for the longest code, that there is one symbol, all right, in the code word tree, which doesn't have a sibling. Do you agree with this? Does everybody agree with this? Hopefully there's no issue with this. Why not? Why does it? Okay, I mean, if you don't want to think about it with the tree, let's take the code word for x. Okay. This is some binary sequence. Okay? And so this has a length greater than all of the others. All right? And what we also know is that this sequence, if I just remove the last bit of the code word, right? So this will give me a new code word, and this code word is not going to be a prefix of any other code word. So firstly, if the encoding of X is say C1, C2 up to CK, then C1 up to CK minus 1. Firstly, this cannot be a code word of any other symbol because it's prefix free. And C1 through CK minus 1 is the prefix, is a prefix of C1 through CK. So this is not a code word, and also cannot be a prefix of any other code word. That's because all of the other code words have length less than or equal to k minus 1. Okay. So even if I delete the kth bit or the last bit, I end up with a new code word which has strictly shorter length than the original code word, and the code is still prefix free. So I've just reduced the expected length of the code by deleting the last code word bit for the symbol X.
This is only for the longest.
This is only for the longest, nothing else. But nevertheless, the expected length is now going to strictly decrease. So from the old code, I got a new code with smaller expected length, which must mean that the old code cannot be optimal.
Sir, isn't this statement that two longest code words are same like this trivial? Like, if they are different, then one must be the longest and other cannot be the longest.
Correct.
And then like this, and then
So what if there's only one longest code word? That's the point, right? What happens if there's only one longest code word? When I say two longest code words, it doesn't mean that both code words have to have the same length. When I just simply say two longest code words, they can have different lengths. So if I sort the lengths in decreasing order, then the last two lengths. That's what I mean when I say the two longest code words. All right. So in terms of definition, there is no problem. But what this says is that they can't have different lengths, because if they were to have different lengths, then they cannot be optimal. Then this code cannot be optimal, because I can always reduce the size of the longest code word while still maintaining the property of prefix free. Okay. Is this?
Say anything about the second longest code word that it doesn't have the sibling?
What do you mean the second?
Can I say that second
Yes.
longest code word does not have a sibling?
The second longest code word should have the same sibling. So its sibling should be the longest code word. So the two longest code words should be siblings of each other.
Since that place is empty,
Correct. I could shrink this. Right?
That will not be true.
Which one?
The two longest sequence have to be, two longest code words have to be.
Why not? Can you give me?
All of them are equal length. There
isn't
is
that
no
what third?
order two longest.
Isn't that what third one says?
But okay. So the slightly different way to say this is that there are two longest code words which are siblings of each other. Right. Okay. But the third property says that the two longest code words differ by exactly one bit. And these correspond to the symbols with the least probabilities. The two least probabilities. Now this third property is not something that every optimal prefix-free code has to satisfy. All right. For example, here is a prefix-free code that does not satisfy the third property. So let's say I have A, B, C, D, and A has probability point, say 26, B has probability 0.24, C has probability 0.26, and D has probability 0.24. This is an optimal prefix-free code for this, but it doesn't have this third property because the two symbols with the least probability are B and C, but they're not siblings of each other. They don't differ by 1 bit, they differ by 2 bits. All right. So this is, well, maybe I should have labeled this in a little bit differently. Let's say 0.24, 0.26, 0.26, and 0.24. The code word for A is 00. The code word for D is 11. So they differ by 2 bits. And these are the two least probability symbols. Yeah.
But there is like barring relabelling. If we were to relabel.
Exactly. So, but the point is, just by relabeling this, you can get a code that satisfies the third property. So that's why the statement says there exists an optimal prefix-free code that satisfies all of these 3 properties. So every prefix-free code must satisfy property 1 and property 2, but not every optimal prefix-free code has to satisfy property 3.
Are these also sufficient?
Which one?
These 3? Is any
No.
code-
No, right? Because I can. So I can just the same probabilities. I can just extend the length of two of those. Let's say I have, say this is B, C, D, and A. So this code satisfies the first property because these two symbols have higher probability than these two symbols, but the lengths are less than these two symbols. And the two longest code words have the same length. So I have 1, this is 1, 0. The two longest code words have the same length, 3 and 3, and they correspond to the least probability symbols, which are D and A. Right? But this is not optimal. Questions? So we'll say that a code that satisfies these 3 properties is canonical. All right. Question?
The 3 satisfied all 3 points.
Correct.
Still it is not
It is not optimal, yes. So it means that those three properties are not sufficient, right? They're also not necessary, because the third property is not necessary for every optimal prefix-free code to satisfy. Properties 1 and 2 are necessary for every optimal prefix-free code. Property 3 is not necessary for every optimal prefix-free code. And the three properties put together are not sufficient for an optimal prefix-free code. But all we can say is that there is at least one prefix-free code that satisfies all of the three properties. And for such a code, we'll call it canonical. So from any optimal prefix-free code, we can essentially get a canonical optimal prefix-free code just by relabeling. Okay? So it's enough to just study canonical prefix-free codes. So firstly, hopefully you agree with me that Huffman codes are canonical. Right? Because we're always merging the two least probability symbols. So just by construction, the two least probability symbols will get the same code word length, and they're also going to differ by exactly 1 bit. This is by construction. And again, by construction, if you have two symbols, if one symbol has a higher probability than the other, then the code word length cannot be any larger than the other. Okay? So it satisfies all of 1, 2, 3 properties. But now we want to show that these are also optimal. So we'll essentially follow an induction argument. All right. So let's sort. Okay. So firstly, for any PMF on two symbols, Huffman coding is optimal. Right, it's a trivial statement because all that Huffman coding does for two symbols is assign one symbol bit 0, the other symbol bit 1. That's it. So it's optimal. You can't do any better than that. So let's assume that for any PMF on m-1 symbols, Huffman code is optimal. All right, so in the induction step, we have to show that for any PMF on m symbols, it is optimal. Assuming that it is optimal for any PMF on m-1 symbols. So we'll perform induction on the alphabet size. Okay. So let's take a PMF which has probabilities P1, P2 up to Pm. Okay, we'll assume that P1 is greater than or equal to P2, greater than or equal to so on. So sorted in descending order. All right, and let Cm star be an optimal canonical prefix free code. Okay, any optimal canonical prefix free code for M symbols. All right, and CMH be the Huffman code. Okay, on M symbols. Let's also consider, so let's do the following. Let me merge the last two symbols, M and M minus 1, to form a super symbol. Okay. So let's say Px prime is P1, P2 up to Pm minus 2, and then the last symbol has probability Pm minus 1 plus Pm. Yeah, so this is not really in descending order, but that's okay. So Pm minus 1 plus Pm could potentially be larger than Pm minus 2, but that's fine. So now I have the following claim that if I merge the last two symbols, I get a super symbol. So if I take the Huffman code, let's take the Huffman code on M symbols. I will merge the last two symbols. All right. So now I get a different code tree where these two have been merged to give one node. All right. Now this resulting code tree is going to be a Huffman code for this probability mass function. Do you agree with that point? Because it's the same, it's a recursive procedure. All right. So by merging the last two symbols, or by trimming the last two bits of the Huffman code for the two longest code words, I get another Huffman code for this new distribution. And this new Huffman code is going to be optimal for this particular distribution. Okay. So let Cm minus 1 H be the Huffman code obtained by merging the two longest code words. Okay, this is also going to be a Huffman code. For Px prime. Okay, is everybody okay with this statement? If you want to take a specific example, let's say that this were the Huffman code All right, so 0, 0, 0, 1, 1, 0, 1, 1. And let's say that these two were the least probability symbols. Now by merging the two least probability symbols, I got this code, which is 0, 0, 0, 1, and 1. Okay, that's the procedure. So this original code was a code for 4 symbols. Now I got a new code for 3 symbols. But the point, yeah,
Need not be the Huffman code for the experiment.
it is going to be a Huffman code for Px prime.
And then the way we haven't ordered the experiment,
That's okay.
then how would it,
So the Huffman code is only obtained by merging two least probability symbols, right?
I mean, we merge two least probability symbols and we get a Huffman code again, but it wouldn't be the same code for by merging the two least probabilities in the original.
So for this new probability mass function, how would you construct the Huffman code? What would be the next step?
I mean, what I'm saying is CH of m minus 1 is a Huffman code. But
Correct.
it will not be the Huffman code for this. I mean, we haven't ordered this separate PX. If we ordered PX prime, then we can say that it's a Huffman code for PX prime.
But why does ordering have to play a role? You're anyway going to merge the two least probability symbols irrespective of how this PMF is ordered, right? So the Huffman code for the PMF 0.2, 0.3, 0.2, 0.3 is the same as the Huffman code, at least effectively, up to just relabeling. The Huffman code for 0.3, 0.3, 0.2, 0.2. Right, so the Huffman code is merely determined by the set of probabilities rather than which individual symbols get those probabilities. Do you agree with that point? So here, when I said that this is in descending order, I merely meant it for notational convenience. That's it. Because I just wanted PM and PM minus 1 to have the least probabilities. In fact, the order of the other symbols doesn't matter to me. Okay? Just because I'm saying that I'm merging PM minus 1 and PM. I don't really care how the other symbols are ordered, whether it's in decreasing order or not, it's immaterial. But the only point is that PM minus 1 and PM correspond to the two least probabilities. That's all. Okay. So by merging these two, I get a new probability mass function. And by merging the two code words, I get a new code, which is also a Huffman code, which will be a Huffman code for Px prime. All right. So for Px prime, so that's one code. Now for the optimal code, I have another optimal code for M symbols. Right. So let Cm minus 1. Right. So I have a Cm star. Let Cm minus 1 be obtained by merging the two longest code words of Cm star. So same procedure, okay, but at this point I can't really say that Cm minus 1 is optimal for Px prime. So Cm star is an optimal code for Px, and Cm minus 1 is obtained by merging the two longest code words of Cm prime. Because we've assumed that CM star is a canonical optimal prefix free code. The two longest code words correspond to the two symbols with least probability. So essentially, we've still merged the symbols corresponding to PM-1 and PM to get a new code word. Right? So let's compare the expected lengths of CM star, CM-1, and CMH and CMH-1. So the expected length of CM star minus so let's see by how much does the expected length let's just take a look at this particular difference. This is so first the expected length of CM star. This is summation overall x or summation overall I pi li star right, which I can write as summation I equal to 1 to m minus 2 pi li star plus pm minus 1 plus pm lm minus 1 star minus 1 why? It's a canonical optimal code. Which one? Okay. This summation should be up to m minus 2. Right. Okay. It's a canonical code, so lm minus 1 is equal to lm star is equal to lm minus 1 star. So I can write this. So this is equal to expected length of Cm minus 1 plus Pm minus 1 plus Pm. All right. So mind you, this Cm minus 1 is a prefix-free code. It need not be canonical, it need not be optimal, but Cm minus 1, which is obtained by merging the two longest code words in Cm star, gives me a prefix-free code for m minus 1 symbols. Now, similarly, along the same lines, the expected length of the Huffman code is equal to the expected length of the Huffman code for m minus 1 symbols plus Pm minus 1 plus Pm. Okay? But then what can you say about expected length of Cm minus 1 versus the expected length of the Huffman code on m minus 1 symbols? So this is greater than or equal to the expected length for the Huffman code. Because the Huffman, we've assumed that the Huffman code is optimal for m minus 1 symbols. Right? Just by comparing the two, it must mean that the expected length of Cm star should be greater than or equal to the expected length of the Huffman code on m symbols. Right? Because I have expected length of Cm star equal to expected length of Cm minus 1 plus some quantity. Expected length of the Huffman code on m symbols be equal to the expected length of the Huffman code on m minus 1 symbols plus the same quantity. So this quantity is greater than or equal to this quantity. So this quantity should be greater than or equal to this quantity, which implies that Huffman code is optimal for PX.
So this inequality also means that both of them are equal.
Sorry?
This inequality means that both of them are equal.
Both of them are equal, yes. In fact, one can prove a much stronger statement, which is any optimal prefix free code is length equivalent to Huffman code. Okay, so any questions? All right, so let's stop here.